Hello viewers, here is Dr. Mala Das Sharma. Welcome you to my video number 130 of my channel MALACHEMPHILIC. And video number 130 is the 69th episode of Chemical Thermodynamics, where the topic is activity and activity coefficient for non-ideal solution. So let's start. So activity and activity coefficient. You must be familiar with the term activity. In the electrochemistry, you have observed that if we take one dilute solution of an electrolyte and one moderately concentrated solution, that means not very dilute, of and the same electrolyte, then the conductance will be almost same. That means same amount of current is carried by the ions or same ampere of electricity current is produced. Okay. How concentrated solution means number of ions are more, ions are carrier of electricity. So you should have got the more ampere of current, but it will be almost same for moderately concentrated solution also. There it is explained that by Debye-Huckel theory, that when ions are moving towards that electrode, then the oppositely charged ion drag it from the behind. In concentrated solution, more number of oppositely charged ion will be there, so it will drag it from behind strongly. So what happens? Velocity decreases, so conductance decreases, so we'll get less ampere of current. Okay, that means as if the number ions are carrier of electricity, the number of ions are less in the concentrated solution, or less number of ions even in the moderately concentrated solutions are reaching to the electrode and getting discharged. So the almost same current is obtained for the dilute solution and the moderately concentrated solution. Okay, so it appears that concentration in the moderately concentrated solution is less, or its effective concentration is less. It has produced less number of ions, so less number of ions of the solution goes to the electrode. That effective concentration, we call it as activity. Now here, in case of non-ideal solution, we use the term activity. This activity indicates the effective concentration of the component in solution for non-ideal solution. So activity indicates the deviation from ideal behavior. The relation between chemical potential and the concentration of the ideal solution, concentration on mole fraction, we know that this chemical potential of the ith component in ideal solution, that will be is equal to mu I in the standard state plus I is the component I, RT ln xi. Xi is the mole fraction in the solution. Now the equation for chemical potential in non-ideal solution that is what? That is chemical potential of real solution is equal to same chemical potential of the component in the standard state, that will be same, plus RT ln AI, where the AI is the, say this is my equation number 1 and this is my equation number 2, and my AI is the activity or effective concentration of ith component in non-ideal solution. Right? Now, Next, what we'll do? We'll do equation 2 minus 1. What was my equation 2? Mu real minus equation 1 mu ideal is equal to mu of this ith component in the standard state plus RT ln AI minus mu I in the standard state minus RT ln XI. So from here I can write, look at here, this mu y star cancel. So what can I write? I can write RT ln AI minus RT ln XI, that is equal to mu of ith component, chemical potential of the ith component in real solution minus mu of ideal solution. So this one I can write it as RT ln AI by XI, that is equal to mu real minus mu ideal. Okay. Now this AI by XI, that is denoted by gamma I, known as the activity coefficient, right? Now look at here, from here what can I write? AI is equal to gamma I into Xi, so therefore AI is proportional to X. We can write that this RT ln AI by Xi is equal to, already we have written here, that is mu real minus mu ideal. So ln AI by Xi is gamma I. Gamma I is equal to mu real minus mu ideal divided by RT. RT is constant at constant temperature. So mu real minus mu ideal, that means this is the deviation from ideal behavior. So this activity coefficient gamma I is the measure of deviation from ideality. Now, the activity coefficient is defined as the ratio of concentration of non-ideal solution to that of the ideal solution. Just now we have seen that this gamma I is equal to AI by XI, right? Now, see the situation when gamma I is equal to 1. So from here, therefore, we can write AI is equal to gamma I into Xi. So when gamma I is equal to 1, then AI is equal to Xi. That means effective concentration or effective mole fraction and actual mole fraction are same. That indicates the ideal solution. This indicates ideal solution. Now, second case, when gamma I greater than 1, then what happened? See from the equation. So, AI will be greater than Xi. That indicates non-ideal solution showing positive deviation from ideal behavior. Okay. Now the third situation, here what happened? Non-ideal solution showing positive deviation from Raoult's law or ideal behavior means, these solute-solvent interactions are weaker than solvent-solvent or solute-solute. As these interactions are weaker, they have more escaping tendency. That means components have more escaping tendency. More number of component goes to the vapor phase, so partial vapor pressure of the component increases. So it appears that as if the solution has more concentration, so more amount goes to the vapor phase and it gives the more partial vapor pressure. That means the effective concentration, as if that concentration, it is effective concentration is effective concentration appears as greater than that of the actual concentration. Now, the next case, when gamma I less than 1, then AI less than xi. What is indicated by this? This indicates that non-ideal solution showing negative deviation from ideality. Non-ideal solution showing negative deviation from ideality means this attraction between the solute-solvent molecules are greater than solvent-solvent or solute-solute. So as these attractions are more, less number of molecules of the component can escape to the vapor phase. So less number of molecule of the component are in the vapor phase means partial vapor pressure of the component decreases. That means as if the solution is having less concentration, so less amount of partial vapor pressure it can produce. So effective concentration is less. Okay. Now, so activity is the kind of effective concentration or effective mole fraction, just as fugacity term I'll discuss in the next video, which is related to gas. Fugacity is the effective pressure of the gas. We'll discuss next video. The unit of activity is same as that of concentration because it is the effective concentration only. Next, the activity is the function of temperature, pressure and mole fraction of the components, say x1, x2, x3, etc. Similarly, activity coefficient also the function of temperature, pressure and mole fraction of all the components. Okay. So what we have observed that activity is the effective concentration or effective mole fraction in the non-ideal solution and activity coefficient is the measure of departure from ideal behavior. Hope you have understood. Thank you.